Okay, here are a few assorted examples from Chapter 1, just for some extra practice. Okay, first thing we're going to do is we're going to convert some scientific notation. So if I'm going to do, say I've got this number here, and I want to convert to scientific notation. Okay, so to do that, we put a decimal at the end, and we move it. 1, 2, 3, 4, 5, so I get 2.5 times 10 to the 5th. Another example. So if I go 1, 2, 3, 4, 5, 6, 7. So I have 1 times 10 to the negative 7th. Okay, what we observe is if we move to the left, the number, better known as our exponent, is larger. If we move to the right, exponent is smaller. So just remember that. And it makes sense because this is a large number and this is a small number. So for large, we better expect a large positive. This number's small, so we expect a smaller number, when usually in this case small is negative. Okay. Let's go ahead and now do a unit conversion. Let's convert 275 micrograms to grams. Okay, we're going to do this without the aid of our stair-step handout that I gave you. So, okay, something to note here. Micro is 10 to the negative 6 on our prefix. Gram is our base, so it looks like whatever we're doing 6 steps. Alright, so we have 275 micrograms. I'm going to call it MCG. I put micrograms on the bottom, grams on top. There are 1 gram, 10 to the 6th micrograms. I'll show you an alternative way to do that in just a second. So our final answer is 275 divided by a million, or 275. Okay, here's an alternative way. Let's say there are 10 to the negative 6 grams in 1 microgram. Again, it doesn't matter which way you do it, they both work. So I'm doing scientific notation, 1, 2, 3, 4. 2.75 times 10 to the negative 4 micrograms. Okay, so just bear that in mind. Remember, if we're going up, our unit is going up the stairs. It's becoming smaller. In other words, our number is getting smaller. If we're going down, our unit is getting larger. Okay, now here's one, density. I didn't do any of these, and I should have. So density by displacement. Okay, so what this is if we're trying to determine the density of an object, we can do water displacement before and after. So okay, an example. So we have a grad cylinder. I might have spelled that wrong. Filled with water. Let's just say we have 20 mLs of water. And I can pick any number I want. And if you do this as a lab exercise, pick a nice round number is what I'd advise you to do. So a 7.0 gram object was added, and volume in cylinder, never said I could spell, changed to 22.7 ml. What is density? Okay, so we need a mass and a volume. The mass is easy, that's 7 grams. What's our volume? So what we're looking at here is our change in volume. So we have 22.7, that's our final. Our initial was 20.0 exactly. So now our volume of our object is 2.75 ml. And sometimes the volume will be in different units. A centimeter cubed is the same thing as an ml. So if you're in the health professions, you may hear 20 cc's of whatever drug. This means the same thing as milliliters. Okay, so to finish it off, density is a mass per volume. Our mass is 7 grams. Our volume is 2.7 ml. Okay, we do that, we calculate that. We get 2.59 grams per ml, but we're not done. We have two significant figures, so that's going to become 2.6 grams per ml. So when we're doing a water displacement, the key here is to find the mass, which is usually given. Sometimes you might have to subtract it out. The volume change, and applying our definition of density. Okay, let's do one more. So an object with a density of 2.1 grams per ml is added to 25 mils of H2O in a grad cylinder. Volume changed to 28 ml. What was the object's density? Okay. Just basically what we do here is we apply our definition. So we have D is M over V. Wait a minute, no, we don't need density, we need mass. Nope, given density. My bad. Okay, so if we take a look, we have density is 2.1 grams per ml. We don't know our mass. Our volume is 3 mils. So then we just simply multiply. So for this one, I'm going to ignore significant figures because I only have one and that's just not very good. So I have 6.3 grams. So all we do is multiply, the mils cancel, and I'm left with grams. For the record, if I did want to do significant figures, it would just be 6. Okay, last thing I want to do is a significant figure example where we do multiple operations. So if I had, let's just consider this problem. Okay, so how many significant figures would our final answer have when we've got multiple operations? All we do is we take it one step at a time. So let's do our two parentheses. So 10 minus 2.1 gives us 7.9. And notice I have one decimal place. Okay, and now let's do our addition on the bottom. I get 15.31. Two decimal places. Notice that has 2 and that has 3. Okay, last but not least, we do our division. So 7.9 divided by 15.31 gives us 0.516002. Alright, now, as I've said before and always say, is just go ahead and do the math. Don't let the figures get in the way. Now we determine significant figures. This one has 2. This has 4. As we said in class, smallest number of significant figures dictates. So then this answer now becomes 0.52. So the key here is to do your separate operations and then figure out significant figures at each step, and then at the end you should be fine, and then you don't round until the very, very end. Okay, that should be